This lesson is about simplifying and evaluating expressions with integer and zero exponents. It's lesson 32 in your book on pages 197 through 204. Algebraic expressions can contain exponents that are positive, like the ones we worked with so far, negative, or zero, and these are new concepts that we're talking about in this specific lesson. So like powers of 2, you can have 2 to the 4th, 2 to the 3rd, 2 squared, 2 to the 1st, obviously. But you can also have 2 to the 0th power, or any number to the 0th power, or to the negative 1st, or to the negative 2nd. That's where these properties come into play. So these are properties that you need to know. They are really important, and we're going to use them all the time. So first we have the negative exponent property, and it says for every non-zero number x, x to the negative n power equals 1 over x to the n, and x to the nth power equals 1 over x to the negative n. Now let me give you a numeric example. So say I have 4 to the negative 7th power. That is the same as having 1 over 4 to the positive 7th power. So if I want to make a negative power into a positive, I would move it to the other side of the fraction. So here, this 4 to the negative 7th is in the numerator. If I move it to the denominator, the exponent, and only the exponent, becomes positive. Also, if I have maybe 4 to the 3rd power, then I can say that is the same as 1 over 4 to the negative 3rd power. So moving that expression to the denominator instead of the numerator changes the sign on the exponent. Now, if I have a negative exponent in my denominator and I want to make it positive, I move it into the numerator. The other property that we have is the zero exponent property, and that says that for every non-zero number x, x to the 0th power equals 1. Doesn't matter what x is, if anything is being taken to the 0th power, then it's 1. We're going to use those properties to simplify these expressions here. Now these are examples, so they do need to be in your notebook. First we have x to the negative 3rd power. Now it's never simplified to say that we have a negative power. In math, we always want to make all our powers positive. So we have x to the negative 3rd power, and we need to make this a positive exponent. So this is in the numerator, right? It's kind of like x to the negative 3rd over 1. So if we take x to the negative 3rd and move it into the denominator, that will make our exponent negative. X to the positive 3rd. I'm sorry, that will change the sign and make the exponent positive. Now we have 1 on top. So if you move everything from the numerator into the denominator, then the only thing left in the numerator is 1. And this is your simplified form. In this example here, we have y to the negative 4th over x squared. Now, the x squared in the denominator is fine because it has a positive exponent. But the y to the negative 4th in the numerator is not because it has a negative exponent. So we need to make this negative exponent into a positive exponent. And the way we do that is by moving it from the numerator to the denominator. Now, x squared stays in the denominator because it's positive already and it's fine. And instead of y to the negative 4th, when we move it to the denominator, it's y to the positive 4th. Now, since we moved everything from the numerator into the denominator, the only thing left in the numerator is 1. And this is our simplified form. And finally, we have 1 over w to the negative 4th. Now, we can't have a negative exponent. So in order to make this exponent positive, we need to move this denominator into the numerator. So now we have w, and instead of to the negative 4th, it's to the positive 4th, and then it's times 1. But since anything times 1 is itself, w to the positive 4th will work. Here are some more examples, and again, these need to be in your notebook. It says, evaluate each expression for a equals negative 2 and b equals negative 3. Okay, so I know that I'm going to need to plug these numbers into my expression to evaluate it. But before I do that, see how I have b to the 0th power here? It doesn't matter what b is in this case, because it's to the 0th power, and anything to the 0th power is 1. So I can say that that's the same thing as a squared times 1. And when you multiply a squared by 1, you just get a squared. So all I really need to find here is what is a squared. Now since a is negative 2, I will plug negative 2 in. Make sure you use those parentheses, they're important, and square it. So that would be the same thing as negative 2 times negative 2, which is a positive 4. So that is my solution. Here I have 3b to the negative third times b. Now before I plug any numbers in here, I want to simplify this. So remember how when we are multiplying like bases, we need to add their exponents? So we still have a coefficient of 3 here. Now I have b to the negative third times b to the first, because whenever there's not an exponent there, we assume it's a 1. So I can add these two exponents. So it's the same as b to the negative 3 plus 1. Now negative 3 plus 1 is negative 2. But I can't evaluate a negative exponent, so I need to make that exponent a positive. Now 3 doesn't have a negative exponent, so it's going to stay in the numerator. But b to the negative second has a negative exponent, so I'm going to move it to the denominator and make the exponent positive. Now I can evaluate by plugging negative 3 in for b. So I have 3 over b squared, or negative 3 squared. Now negative 3 squared is 9, and when I reduce 3 over 9 by dividing the top and bottom by 3, I get 1 over 3. So my solution here is 1/3. Now here's another property of exponents. Again, it's one that you really need to know. It's called the quotient property of exponents. If m and n are real numbers and x does not equal 0, and again, x can't equal 0 because check this out, we have x in the denominator. We can't have 0 in the denominator. Then x to the m over x to the n equals x to the m minus n, or 1 over x to the n minus n. Now what this means is that anytime you have a number to a power and a like base to a power being dividing by it, you can subtract those exponents. So when we are multiplying like bases, we add the exponents. When we're dividing like bases, we actually subtract them. So 5 to the 4th divided by 5 to the 2nd is still 5, but it's to the 4 minus 2. So 5 squared, which is 25. Also, if we have 5 squared divided by 5 to the 4th, we subtract those exponents. Another way you might look at this is you would have 5 to the 2 minus 4, which is 5 to the negative second power. And again, since it has a negative exponent, you have to move it into the denominator, so it's 1 over 5 squared, which is 1 over 25. Alright, so here are some examples. These need to be in your notebook. Here I have x to the 7th divided by x to the 3rd. These are like bases. We're taking x to a power, and we are dividing these like bases. When we divide like bases, we subtract their exponents. So I still have x, which is what I'm dividing, my base, but I'm going to take it to be 7 minus 3 power. So you always take the top number minus the bottom number. Now that means that we have x to the 7 minus 3rd, which is 4. So this simplified is x to the 4th power. Now this makes sense, because if we had x to the 7th power, that means we have x 7 times, right? 1, 2, 3, 4, 5, 6, 7. And we're dividing it by 3 x's. So that means that 3 of our pairs of x's on the top and on the bottom are going to cancel out, and we have 4 x's left. That's where we get that x to the 4th. Alright, now here we have x to the 3rd divided by x to the negative 7th. Now, we can't have a negative exponent. We never want to do that. But in this case, we're going to wait and simplify it later. So I have like bases, which is x, and I am dividing them so I can subtract their exponents. That means I have 3 minus my bottom exponent, which is negative 7. Now, minus and negative means that we're really adding. So I actually have x to the 3 plus 7 power. and 3 plus 7 is 10. So this simplifies to x to the 10th power. Now, here you could also say, okay, I've got 3 x's on top, and then here I have x to the negative 7th, so I'd have to move that into the denominator, and that means I'd have positive 7 x's. So in total, I have 10 x's that I'm multiplying, so it's x to the 10th power. And in this example, I have several different bases, but I'm still, to a point, dividing like bases. See, here I have x to the negative 5th, and then down here I have x to the 1st. Those are like bases, so I can subtract their exponents. So I have x to the negative 5 minus 1. I also have y's. I have y to the 6th on top, y to the 2nd on bottom. So that's y to the 6th minus 2, top exponent minus the bottom. And then I also have 2 z's. I have z to the 1st, and on the bottom z to the negative 3rd. So I have z to the 1 minus negative 3. Now when I simplify this, it gives me x to the negative 5 minus 1 is negative 6, y to the 6 minus 2, which is 4, and z to the 1 minus negative 3. Since I'm subtracting a negative, I'm really adding, so it's z to the 4th. But it's not simplified all the way here, because x has a negative exponent. Now y to the 4th and z to the 4th are fine in the numerator because they have positive exponents. But I need to move this x into the denominator. So I still have y to the 4th, z to the 4th. And in the denominator, I have x to the positive 6th power. And that's my solution there. Now for our last example that needs to be in your notebook. The intensity of sound can be measured in watts per square meter. The table below lists the intensity levels for some common sounds. So we have the rocket lift-off, jet lift-off, down to a soft whisper. What they want to know is how many times more intense is the sound of a rocket lift-off than that of regular speech. So they want us to express the answer in exponential and standard form. Now we're going to have to take the intensity of a rocket liftoff, which is 10 to the 3rd, and divide it by, because we want to know how many times bigger it is, the intensity of regular speech, which is 10 to the negative 7th. Since we have like bases here, they're both 10. They don't have to be variables for this to work. We have like bases, which are both 10. I still am going to have 10, but since I'm dividing, I can subtract their powers. So top power, 3rd, minus the bottom power, negative 7. Now, 3 minus negative 7 is really 3 plus 7, right? So I have 10 to the 10th. Now, this is my answer expressed in exponential form. However, they also want it expressed in standard form. So I have to take 10 to the 10th power. Now what that means is that I am going to have a 1 with 10 zeros. So it would be 1 and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then again, commas every 3rd. So I have 10 billion times more intense. And that's it. Thanks for watching.